Tonight, we're going to confront one of the most dangerous puzzles in all of physics. Right now, inside every atom of your body, positively charged protons are packed together so tightly they're almost touching. And every single one of them is trying to push the others away. The electromagnetic force between them is enormous, violent, and relentless. By every law of electricity you've ever learned, those protons should explode apart. Your atoms should tear themselves to pieces. And yet, they don't. Something is holding them together. Something powerful enough to overpower electromagnetism itself at close range. But here's what's truly strange. The force doing this isn't the one most people think it is. It's something subtler, something borrowed, something that technically shouldn't even exist outside the proton. And it's carried by a particle most people have never heard of. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, but probably haven't thought deeply about. You know that magnets have poles. You know that if you try to push two north poles together, they resist. They push back. The closer you force them, the harder they fight. You felt this with your own hands. That invisible cushion of resistance between two magnets that refuse to come together. Now, that force you feel between magnets is electromagnetic. It's the same fundamental force that governs electric charges. And one of the most basic rules of electromagnetism, something you probably learned in school, is that charges repel. Positive pushes away positive, negative pushes away negative. Only opposite charges attract. This seems like a simple rule, almost trivially simple. But if you follow this rule to its logical conclusion inside the atomic nucleus, you arrive at a crisis so severe that it threatened to unravel everything physicists thought they understood about the structure of matter. Here's the problem. The nucleus of an atom contains protons. Every proton carries a positive electric charge. In a hydrogen atom, there's only one proton sitting alone in the nucleus, so there's no issue. But hydrogen is the simplest atom in the universe. Every other element has more than one proton in its nucleus. Helium has 2, carbon has 6, oxygen has 8, iron has 26, gold has 79, uranium has 92, and in every single one of these atoms, those protons are packed together in an almost unimaginably small space. The nucleus of an atom is tiny. Not just small, tiny in a way that's genuinely difficult to comprehend. If an atom were the size of a football stadium, the nucleus would be smaller than a grain of sand sitting at the center of the field. The diameter of a typical atomic nucleus is on the order of a few femtometers. 1 femtometer is 1 quadrillionth of a meter. That's a decimal point followed by 14 zeros, and then a 1. The number is so absurdly small that writing it out barely helps. It's a distance so short that light, traveling at 300,000 kilometers per second, crosses it in about 3 times 10 to the negative 23 seconds. These distances and time intervals don't correspond to anything in human experience. They exist only in the subatomic world, the world inside the nucleus. And in this impossibly tiny space, protons are crammed together almost shoulder to shoulder, each one carrying a positive electric charge, each one repelling every other one with a force that obeys Coulomb's law. Coulomb's law tells you exactly how strong the electromagnetic repulsion is between two charged particles. The force is proportional to the product of their charges and inversely proportional to the square of the distance between them. That inverse square relationship is critical. It means that as you halve the distance, the force doesn't just double, it quadruples. Cut the distance to a third and the force increases by a factor of 9. Cut it to a tenth and the force increases by a factor of 100. The closer the charges get, the more violently the force increases. And inside the nucleus, the distances are extraordinarily small, which means the repulsive forces are extraordinarily large. Let's put some numbers on this to make it concrete. Consider 2 protons sitting next to each other inside a nucleus, separated by about 1 femtometer. The electromagnetic repulsive force between them is roughly 230 newtons. That might not sound like much until you realize what we're talking about. 230 newtons is about 50 pounds of force. 2 particles so small that trillions could fit on the period at the end of a sentence are pushing each other apart with a force equivalent to a 50-pound weight. The acceleration that force would produce on a free proton is on the order of 10 to the 29th meters per second squared. For comparison, the acceleration due to gravity at Earth's surface is about 9.8 meters per second squared. The electromagnetic repulsion between 2 protons in a nucleus is roughly 100 billion times stronger than gravity at Earth's surface. This is the scale of the problem. This is what the nucleus is dealing with every single moment of its existence. And it gets worse. In a real nucleus, there isn't just one pair of protons repelling each other. In carbon, there are 15 distinct repulsive pairs. In iron, 325. In uranium, 4,186 pairs of protons, all pushing away from each other simultaneously. The total electromagnetic repulsion trying to blow apart a uranium nucleus is an enormous amount of energy concentrated in a space smaller than anything you've ever seen or could ever see. Now, you might wonder whether gravity could hold the nucleus together. After all, gravity holds planets in orbit around stars. It holds galaxies together. It shapes the entire large-scale structure of the universe. Surely gravity must play some role inside the atom, but it doesn't. Not in any meaningful way. Gravity is absurdly weak compared to electromagnetism at the subatomic scale. The gravitational attraction between 2 protons is about 10 to the 36 times weaker than their electromagnetic repulsion. That's a factor of 1 followed by 36 zeros. If the electromagnetic repulsion between 2 protons were represented by the distance from Earth to the edge of the observable universe, the gravitational attraction would be smaller than the width of a single atom. Gravity is completely and utterly irrelevant inside the nucleus. It contributes nothing. It might as well not exist at the scale of protons and neutrons. So gravity can't hold the nucleus together. Electromagnetism is actively tearing it apart. And those were the only 2 forces known to physics in the early 20th century. Which meant that when physicists first discovered that atomic nuclei existed and contained multiple protons packed into an impossibly small space, they were confronted with a genuine crisis. The nucleus shouldn't exist. By every known law of physics, it should fly apart the instant it forms. And yet, it doesn't. Atoms are stable. Nuclei hold together. Matter exists. You exist. Something must be holding those protons together. Something powerful enough to overpower the electromagnetic repulsion at nuclear distances. Something completely unknown. The discovery that set this crisis in motion happened in 1911, when Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden performed one of the most famous experiments in the history of physics. They fired alpha particles at a thin sheet of gold foil. The prevailing model of the atom at the time, the Thomson model, imagined the atom as a diffuse blob of positive charge with electrons scattered throughout. If that model were correct, the alpha particles should have passed through with only minor deflections. Most did, but a small fraction, roughly 1 in every 8,000, bounced back at extreme angles. Some came almost straight back toward the source. Rutherford later said it was as if you fired an artillery shell at a piece of tissue paper and it came back and hit you. A diffuse blob of charge couldn't deflect a fast-moving alpha particle backward. Only a concentrated, dense, massive object could do that. Rutherford concluded that the atom's positive charge and most of its mass were concentrated in an incredibly small, dense core. He called it the nucleus. This gave us the modern picture of the atom, but also created the problem we've been discussing. If all the positive charge is concentrated in the nucleus, then for any atom heavier than hydrogen, multiple positive charges are packed into an extremely small volume. And those charges should repel each other violently. This was a revolutionary discovery. It gave us the modern picture of the atom, a tiny dense nucleus surrounded by a cloud of orbiting electrons. But it also created the problem we've been discussing. If all the positive charge of the atom is concentrated in the nucleus, then for any atom heavier than hydrogen, multiple positive charges are packed into an extremely small volume. And those charges should repel each other violently. The nucleus should be unstable. It should explode. Rutherford himself was aware of this problem. He knew that something must be holding the nucleus together. Some force that was stronger than electromagnetism at very short distances. But he didn't know what it was. Nobody did. For years after the discovery of the nucleus, this remained one of the great unsolved puzzles of physics. What is the nature of the force that binds protons together inside the nucleus, despite their ferocious electromagnetic repulsion? The problem deepened in 1932 when James Chadwick discovered the neutron. Neutrons are particles with almost the same mass as protons, but with no electric charge. They're electrically neutral, which is where the name comes from. Chadwick's discovery revealed that the nucleus contains not just protons but also neutrons, and in most atoms, roughly equal numbers of each. A carbon-12 nucleus, for example, contains 6 protons and 6 neutrons. An iron-56 nucleus contains 26 protons and 30 neutrons. Uranium-238 contains 92 protons and 146 neutrons. The discovery of the neutron was important for several reasons. First, it explained why atomic masses didn't match up neatly with the number of protons. Before the neutron was discovered, physicists couldn't fully account for the mass of nuclei. The neutron provided the missing mass. Second, it made the nuclear binding puzzle even more interesting because it turned out that the force holding the nucleus together doesn't just act between protons. It acts between protons and neutrons, and between neutrons and other neutrons with roughly the same strength. Neutrons have no electric charge. They don't participate in electromagnetic interactions in the way that protons do. There's no electromagnetic repulsion between two neutrons, and there's no electromagnetic repulsion between a neutron and a proton. And yet the force that binds the nucleus treats protons and neutrons almost identically. It pulls a proton toward a neutron just as strongly as it pulls a neutron toward another neutron, or a proton toward another proton. The discovery of the neutron also revealed something deeply important about nuclear stability. Neutrons aren't just passive bystanders sitting inside the nucleus alongside protons. They're essential structural components. Without them, nuclei simply cannot exist beyond hydrogen. Think about why this is the case. A proton contributes two things to a nucleus. It contributes nuclear attraction through the strong force pulling on its neighboring nucleons, but it also contributes electromagnetic repulsion, pushing away every other proton in the nucleus. A proton is both a benefit and a liability. A neutron, on the other hand, contributes only one of these things. It contributes nuclear attraction through the strong force, pulling on its neighbors just as effectively as a proton does. But it contributes zero electromagnetic repulsion, because it carries no electric charge. A neutron is pure benefit with no liability. It's like adding structural support to a building without adding any weight. This is why neutrons are indispensable. They provide binding without repulsion. They add to the attractive force holding the nucleus together without adding to the repulsive force trying to tear it apart. In a sense, neutrons are the glue that makes complex nuclei possible. Without them, a nucleus could contain at most one proton, because two protons crammed into nuclear distances would experience enormous electromagnetic repulsion with insufficient attraction to compensate. Consider a hypothetical nucleus of two protons and no neutrons. This would be helium-2, sometimes called a diproton. The two protons attract each other through the strong force, but they also repel each other through electromagnetism. And there's an additional problem from quantum mechanics. Protons are fermions, particles that obey the Pauli exclusion principle. Two identical protons with the same spin orientation cannot occupy the same quantum state. This constraint weakens the attractive force between them compared to what a proton-neutron pair experiences. The result is that helium-2 is unbound. It falls apart almost the instant it forms. The electromagnetic repulsion and quantum mechanical constraints overwhelm the strong attraction. Two protons alone cannot form a nucleus, but add one or two neutrons and everything changes. Helium-3, with two protons and one neutron, is stable. Helium-4, with two protons and two neutrons, is extraordinarily stable, one of the most tightly bound nuclei in all of nature. The neutrons provide additional strong force attraction without any additional electromagnetic repulsion. They fill different quantum states from the protons, allowing the nucleons to arrange themselves in configurations that maximize the attractive interaction. The neutrons are doing the heavy lifting of nuclear stability. This pattern continues throughout the periodic table. For light elements up to about calcium, the most stable nuclei tend to have roughly equal numbers of protons and neutrons. Carbon-12 has 6 protons and 6 neutrons. Oxygen-16 has 8 protons and 8 neutrons. This equal ratio maximizes the strong force attraction because the proton-neutron interaction is particularly favorable due to the charge exchange, mechanism we'll explore later. But as nuclei get heavier, the number of neutrons begins to exceed the number of protons, and the excess grows with increasing atomic number. Iron-56 has 26 protons, but 30 neutrons. Lead-208 has 82 protons, but 126 neutrons. Uranium-238 has 92 protons, but 146 neutrons. The neutron-to-proton ratio climbs from 1 to 1 in light nuclei to about 1.6 to 1 in the heaviest naturally occurring elements. This happens because as nuclei grow, electromagnetic repulsion between protons grows relentlessly. Each additional neutron provides strong force attraction without adding electromagnetic repulsion. The extra neutrons dilute the proton concentration, maintaining binding while reducing average repulsion. Heavy nuclei need a surplus of neutrons just to survive. This is also why there's a limit to how many protons you can put in a single nucleus. Beyond about 120 protons, even an enormous excess of neutrons can't compensate for the electromagnetic repulsion. The nucleus becomes unstable no matter how many neutrons you add. The strong force, powerful as it is, simply can't keep up. This was a powerful clue. Whatever force was holding the nucleus together, it didn't care about electric charge. It was something entirely different from electromagnetism. It was a new force, a force that had never been observed or predicted before the discovery of the nucleus. A force that operated only at extremely short range and was completely invisible at the distances of everyday experience. Physicists began calling it the strong force, and for good reason. At nuclear distances, this force had to be strong enough to overpower the electromagnetic repulsion between protons. That meant it had to be significantly stronger than electromagnetism. In fact, at distances of about 1 femtometer, the strong nuclear force is roughly 100 times stronger than the electromagnetic force. This is why it's called the strong force. It's not a creative name, but it's an accurate one. Within the nucleus, it dominates everything else. But the strong force also had a peculiar property that distinguished it from both gravity and electromagnetism. It was short range, extremely short range. Gravity and electromagnetism both have infinite range. The gravitational pull of the sun extends across the entire solar system and beyond. The electromagnetic force between two charged particles decreases with distance but never actually reaches zero, no matter how far apart they are. The strong force was different. It was effectively zero, beyond a distance of a few femtometers. If you moved two protons apart by more than about 2 or 3 femtometers, the strong attractive force between them vanished almost completely, leaving only the electromagnetic repulsion. At distances much larger than a few femtometers, protons behave as if the strong force doesn't exist. They just see each other's positive charge and repel. This short range explained something important about nuclei. It explained why large nuclei are less stable than medium-sized ones. In a small nucleus, every proton is close enough to every other proton and neutron to feel the strong attractive force. The attraction overwhelms the repulsion, and the nucleus is tightly bound. But in a large nucleus, protons on opposite sides are too far apart to feel each other's strong force attraction. They're separated by more than a few femtometers, so the strong force between them is negligible. But they still feel each other's electromagnetic repulsion, because electromagnetism has infinite range. In a very large nucleus, the protons on one side are repelling the protons on the other side electromagnetically. But they're not attracting each other through the strong force, because they're too far apart. This is why very heavy nuclei, like uranium and plutonium, are unstable. The electromagnetic repulsion, which extends across the entire nucleus, eventually starts to win against the strong force, which only acts between nearest neighbors. This is why radioactive decay exists. This is why nuclear fission is possible. This is why uranium atoms can split apart and release enormous amounts of energy. But we're getting ahead of ourselves. The question in the 1930s wasn't about nuclear stability curves or fission. The question was simpler and more fundamental. What is this force? Where does it come from? What carries it? How does it work? In physics, forces between particles are carried by other particles. This is one of the deepest ideas in modern physics, the concept of force mediation. Electromagnetism is carried by photons. When two charged particles interact electromagnetically, they exchange virtual photons. These photons are the carriers, the messengers, the mediators of the electromagnetic force. You never see them directly in this role because they're virtual particles, existing only for the briefest instant as they pass between the interacting charges. But they're real in the sense that they produce measurable effects. Every electromagnetic interaction you've ever experienced, from the light entering your eyes right now, to the repulsion between two magnets, to the chemical bonds holding your body together, all of it is mediated by photon exchange. Gravity, according to our best theoretical understanding, should be mediated by a particle called the graviton. We haven't detected gravitons directly because gravity is so weak that individual gravitons are almost impossible to observe. But the theoretical framework predicts their existence. So if electromagnetism has a carrier particle, the photon, then the strong nuclear force should have a carrier particle too. Some particle must be passing between protons and neutrons inside the nucleus, carrying the attractive force that holds them together. But what particle? What were its properties? How massive was it? How did it behave? This was the question that a young Japanese physicist named Hideki Yukawa asked himself in the early 1930s, and his answer would change the course of nuclear physics forever. Yukawa realized that he could deduce the properties of the carrier particle from the known properties of the force it carried. He knew the strong nuclear force was short range, effective only over distances of a few femtometers. And he knew from quantum field theory that the range of a force is inversely related to the mass of its carrier particle. This relationship is one of the most elegant and powerful ideas in physics. If the carrier particle is massless, like the photon, the force has infinite range. That's why electromagnetism reaches across the universe. If the carrier particle has mass, the force drops off exponentially with distance, and the heavier the carrier, the faster it drops off. The range of the force is inversely proportional to the carrier's mass. A heavier carrier means a shorter range. Yukawa worked the calculation backward. He knew the range of the strong nuclear force, approximately 1 to 2 femtometers. Using the relationship between range and carrier mass, he calculated that the carrier particle must have a mass of roughly 200 times the mass of an electron. This put it squarely between the electron and the proton in mass, in a range where no known particle existed at the time. Yukawa published his prediction in 1935. He proposed that a new particle with this specific mass must exist, and that it was responsible for mediating the strong nuclear force between protons and neutrons. He called it the meson, from the Greek word mesos, meaning middle, because its mass was in the middle range between the light electron and the heavy proton. Initially, many physicists were skeptical. Proposing a new particle to solve a problem seemed speculative, maybe even desperate. But Yukawa had done more than just guess. He had made a precise, testable prediction. The particle should have a specific mass. It should exist in nature. And if physicists looked hard enough, they should be able to find it. Then something happened that led to years of confusion. In 1936, Carl Anderson and Seth Neddermeyer discovered a new particle in cosmic rays with a mass close to Yukawa's prediction, about 207 times the mass of the electron. Physicists excitedly announced that Yukawa's meson had been found, but this particle didn't interact strongly with nuclei. It passed through matter almost as easily as empty space. It interacted far too weakly to be the nuclear force carrier. This particle, which we now call the muon, turned out to be a heavier cousin of the electron with no role in the strong force. As physicist Isidore Rabi famously quipped, it was something nobody had ordered. The true carrier particle was still missing. It wasn't until 1947 that the real carrier was found. Cecil Powell and his team at the University of Bristol, using photographic emulsions exposed to cosmic rays at high altitude, detected a new particle that was distinct from the muon. This particle had a mass of about 270 times the mass of the electron, close to Yukawa's prediction. And critically, it interacted strongly with atomic nuclei. When it encountered a nucleus, it was absorbed quickly, exactly as Yukawa's theory demanded. This was the Pion, the true meson that Yukawa had predicted 12 years earlier. Its discovery was a triumph of theoretical physics, a case where a particle was predicted from pure reasoning about the nature of forces and then confirmed by experiment. Yukawa was awarded the Nobel Prize in Physics in 1949, the first Japanese citizen to receive a Nobel Prize. Powell received the Nobel Prize in 1950 for his experimental discovery of the Pion. But discovering the Pion was only the beginning. Knowing that it existed and that it mediated the nuclear force was one thing. Understanding what it actually was, how it worked, why it had the properties it had, that was a much deeper question, and answering it would require diving inside the proton itself, into a world of quarks and gluons, and a force so strange that it defied almost everything physicists thought they understood about how nature works. Because here's the thing that makes this story so remarkable. The force that holds the nucleus together, the force carried by pions, isn't actually a fundamental force at all. It's a residual effect, a leftover, a shadow of something deeper and more powerful happening inside the protons and neutrons themselves. To understand the pion, to truly understand why the nucleus holds together, you have to go inside the proton. And what you find there is one of the strangest and most beautiful things in all of physics for most of the 20th century. Protons and neutrons were considered fundamental. They were thought to be the smallest building blocks of matter, indivisible particles with no internal structure. This made intuitive sense. If you couldn't break something apart, if no experiment you could devise could split it into smaller pieces, then it seemed reasonable to conclude that it was elementary, that it had no parts, that it was, in the most literal sense, a point-like thing with no inside. But nature had other plans. Starting in the late 1960s, experiments at particle accelerators began revealing something extraordinary. When physicists slammed high-energy electrons into protons at the Stanford Linear Accelerator Center, the electrons scattered in patterns suggesting they were hitting small, hard objects inside the proton. It was eerily reminiscent of Rutherford's gold foil experiment. The physicists who led this work, Jerome Friedman, Henry Kendall, and Richard Taylor, shared the 1990 Nobel Prize for their discovery. What they found confirmed a theoretical prediction that had been made a few years earlier by Murray Gell-Mann, and, independently, by George Zweig. In 1964, both Gell-Mann and Zweig had proposed that protons, neutrons, and a whole zoo of other particles discovered in cosmic ray experiments and accelerator collisions were not fundamental at all. They were made of smaller constituents, which Gell-Mann named quarks. According to this model, a proton is made of 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. The up quark carries a charge of plus 2/3, the down quark minus 1/3. Add up the charges in a proton and you get plus 1. Add them up in a neutron and you get 0. The math worked beautifully. But quarks introduced a mystery that was in some ways even deeper than the one they solved. If protons are made of the quarks, what holds the quarks together inside the proton? And why can't you ever isolate a single quark? Because that's one of the strangest facts in all of particle physics. No one has ever observed a free quark. Not once. Not in any experiment, not in any cosmic ray shower, not anywhere in the universe as far as we can tell. Quarks are always found locked inside composite particles like protons and neutrons. You can smash a proton with enormous energy, and you'll produce a shower of new particles, but none of those particles will be a naked, isolated quark. Every quark that emerges from the collision immediately gets bound up with other quarks to form new composite particles. It's as if quarks are imprisoned, locked away inside their composite particles, with no possibility of escape. This property is called confinement, and it's one of the most remarkable features of the strong force. To understand confinement, you need to understand what holds quarks together inside the proton. And what holds them together is a force mediated by particles called gluons. Gluons are the fundamental carriers of the strong force. They play a role analogous to photons in electromagnetism. Just as photons mediate the electromagnetic force between electrically charged particles, gluons mediate the strong force between particles that carry a different kind of charge called color charge. Now, color charge has nothing to do with actual colors. The name is a metaphor. Physicists chose it because the mathematics of color charge has a loose analogy to how colors combine in optics, but the analogy shouldn't be taken too literally. Color charge is a property of quarks, a quantum number that determines how they interact via the strong force. There are 3 types of color charge, conventionally called red, green, and blue. Every quark carries one of these 3 color charges. Antiquarks carry the corresponding anticolors, called anti-red, anti-green, and anti-blue. The rule is simple but absolute. Every observable particle must be color neutral. It must have no net color, charge. There are 2 ways to achieve this. You can combine 3 quarks, one of each color, red plus green plus blue, which is color neutral, just as combining red, green, and blue light produces white light. This gives you a baryon, and protons and neutrons are both baryons. Alternatively, you can combine a quark and an antiquark, whose colors cancel out, such as red and anti-red. This gives you a meson. Pions, as we'll see later, are mesons. But you can never have a particle with uncancelled color charge. A single quark carrying a single color can never exist in isolation. It must always be part of a color-neutral combination. This is confinement, and it arises from the extraordinary behavior of gluons. In electromagnetism, photons carry no electric charge. They mediate the electromagnetic force, but don't feel it themselves. A photon passes through an electric field without being deflected. This makes electromagnetism relatively simple because the force carriers don't interact with each other. Gluons are radically different. Gluons themselves carry color charge. Each gluon carries a combination of a color and an anticolor. This means gluons interact with each other. They don't just carry the strong force between quarks, they also feel the strong force themselves. A gluon can emit another gluon, which can emit another gluon, which can emit yet another. The force carriers are interacting with each other in a cascading web of interactions that makes the strong force extraordinarily complex. This self-interaction of gluons leads to a behavior completely unlike anything in electromagnetism. In electromagnetism, the force between two charged particles decreases as they move apart. Double the distance and the force drops to a quarter. The electric field lines spread out into space, thinning as they go. The farther apart the charges, the weaker the attraction or repulsion. This is familiar and intuitive. The strong force between quarks does the opposite. As you try to pull two quarks apart, the force between them doesn't decrease. It stays roughly constant or even increases. The gluon field lines between quarks don't spread out into space like electric field lines do. Instead, they get squeezed into a narrow tube, a flux tube connecting the two quarks. As you pull the quarks apart, the tube stretches, but it doesn't thin out. The energy stored in the tube increases proportionally with its length. You're essentially stretching a string, and the farther you stretch it, the more energy you pour into it. This has a profound consequence. If you try to pull a quark out of a proton by pumping in energy, you're stretching the gluon flux tube connecting that quark to the others. The energy stored in the tube increases and increases and increases. Eventually, you've put in so much energy that something dramatic happens. The energy in the stretch tube becomes large enough to create a new quark-antiquark pair out of the vacuum. The tube snaps, and instead of getting a free quark, you get two new composite particles. The original quark pairs up with the newly created antiquark, and the newly created quark pairs up with the quarks left behind. You started with one proton and tried to pull out a quark. You ended up with two composite particles and 0 free quarks. This is why quarks can never be isolated. The very act of trying to separate them creates new quarks that immediately form new bound states. It's like trying to isolate the north pole of a magnet by cutting it in half. You don't get a separate north pole and south pole. You get two smaller magnets, each with its own north and south pole. No matter how many times you cut, you can never isolate a single pole. Quarks are similar. No matter how much energy you pump in, you can never pull one free. This behavior has been confirmed experimentally countless times. At particle accelerators like the Large Hadron Collider at CERN, physicists routinely smash protons together at enormous energies. When two protons collide, the quarks and gluons inside them interact violently. Quarks are knocked out of their parent protons with tremendous energy, but they never emerge as free quarks. Instead, each ejected quark immediately produces a spray of new particles, a jet, as the stretched gluon field fragments into quark-antiquark pairs that combine into observable particles like pions, kaons, and other mesons and baryons. These jets are one of the most distinctive signatures of quark confinement. They're visible proof that quarks cannot exist alone. Now, here's something about the proton that most people find genuinely surprising when they first encounter it. The quarks inside a proton are incredibly light. An up quark has a mass of only about 2.2 mega electron volts. A down quark has a mass of about 4.7 mega electron volts. If you add up the masses of the 3 quarks inside a proton, 2 ups and 1 down, you get roughly 9.1 mega electron volts. But the proton's total mass is about 938 mega electron volts. The quarks account for less than 1% of the proton's mass. Less than 1%. So where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the gluon field and the kinetic energy of the quarks and gluons rattling around inside the proton. Einstein's famous equation, E equals mc squared, tells us that energy and mass are equivalent. They're different forms of the same thing. The intense activity inside the proton, the gluons being emitted and absorbed, the quarks bouncing around at nearly the speed of light, the gluon flux tubes vibrating and fluctuating, all of this activity carries enormous energy, and that energy manifests as mass. The proton is heavy not because its quarks are heavy, but because the strong force binding those quarks is so powerful that the energy of the binding itself outweighs the quarks by a factor of roughly 100. This is a staggering fact. Almost all the mass of every atom in your body comes not from the fundamental particles themselves, but from the energy of the strong force. When you step on a scale, over 99% of your weight is the energy of gluon interactions inside your protons and neutrons. You are, quite literally, made mostly of force. The substance of your body is the energy of the strong interaction manifesting as mass through Einstein's equivalence of mass and energy. The theory that describes all of this, the theory of quarks, gluons, and the color force, is called quantum chromodynamics, or QCD. The name comes from chroma, the Greek word for color, because the force is based on color charge. QCD is one of the pillars of the standard model of particle physics, our best and most complete description of the fundamental forces and particles of nature. QCD is extraordinarily well tested. Its predictions have been confirmed by thousands of experiments, over decades. The existence of quarks, the properties of gluons, the phenomenon of confinement, the structure of jets in particle collisions, the masses of composite particles, all of these are described by QCD with remarkable precision. It's one of the most successful theories in the history of science, but QCD is also extraordinarily difficult to work with. The equations are so complex that in many cases they can't be solved analytically. Instead, physicists use enormous supercomputers to simulate QCD numerically through a technique called lattice QCD, dividing space and time into a grid and computing the behavior of quarks and gluons. Even with modern supercomputers, these calculations can take months or years. The difficulty arises directly from gluon self-interaction. Because gluons interact with gluons which interact with more gluons, the calculations become nightmarishly complex, requiring an infinite cascade of interactions to be accounted for. Despite this complexity, the essential physics is clear. Quarks abound inside protons and neutrons by the exchange of gluons. The color force carried by gluons is so powerful that quarks can never escape, and the energy of this binding is what gives protons and neutrons most of their mass. But now we come to the central puzzle, the puzzle that connects everything we've discussed so far to the question we started with, the question of what holds the nucleus together. Gluons bind quarks inside protons. Gluons bind quarks inside neutrons. But do gluons also bind protons to neutrons inside the nucleus? Is it gluons that hold the nucleus together? The answer is no. And understanding why not is crucial to understanding the pion and the residual strong force. Gluons are confined inside individual protons and neutrons just as surely as quarks are. Remember, gluons carry color charge. They're subject to the same confinement rules as quarks. A free gluon, one that exists outside of a color-neutral composite particle, has never been observed. Gluons cannot propagate freely through space from one proton to another. They're trapped inside the nucleon that contains them. Think about it this way. A proton is color neutral. Its 3 quarks carry red, green, and blue color charges that combine to produce no net color. The gluons inside are constantly being exchanged between these quarks, maintaining the binding. But the proton as a whole presents a neutral face to the outside world. From outside the proton, you can't see the individual colors of the quarks. You can't see the gluons. All you see is a color-neutral particle. It's analogous to an electrically neutral atom. A sodium atom has 11 positive charges in its nucleus and 11 negative charges in its electron cloud. From far away, these charges cancel. The atom appears neutral. You don't see the individual charges unless you get close enough to probe the atom's internal structure. Similarly, a proton appears color neutral from outside. Another proton sitting nearby doesn't see individual quarks or gluons. It sees a color neutral object. And since gluons only interact with color-charged particles, a gluon inside one proton has no reason to reach out and grab onto another proton. The other proton is color neutral. The gluon can't see anything to grab. This is the critical distinction. The fundamental strong force, the color force carried by gluons, operates inside protons and neutrons. It binds quarks into nucleons, but it does not directly operate between protons and neutrons. Gluons do not jump from one proton to another across the nucleus. They can't. They're confined. And yet, the nucleus holds together. Protons and neutrons attract each other with a powerful force that overcomes electromagnetic repulsion. Something is binding them. If it's not gluons directly, what is it? The answer is that the nuclear force between protons and neutrons is a residual effect of the color force. It's not the color force itself. It's what leaks out, a leftover, a shadow, something that shouldn't be there based on the simple picture of color-neutral protons, but is there because the real situation is more subtle than the simple picture suggests. Here's the key insight. A proton is color neutral overall, but its color charge is not uniformly distributed. The 3 quarks inside the proton are not sitting still at fixed positions. They're moving around at nearly the speed of light, jittering and vibrating within the confines of the proton. At any given instant, the distribution of color charge inside the proton is lumpy and asymmetric. One side of the proton might momentarily have a slight excess of red color charge, while the other side has a slight excess of anti-red. These fluctuations are tiny and transient, but they're real. When 2 protons or a proton and a neutron are close enough together, close enough that their internal structure starts to matter, these fluctuations can interact. A momentary excess of color, charge on one side of a proton can interact with a momentary excess on the facing side of a neighboring neutron. The interaction is weak compared to the full color force between quarks because it's a residual effect, a second-order interaction between fluctuations in nominally neutral objects. But at nuclear distances within a few femtometers, it's strong enough to overcome electromagnetic repulsion and bind nucleons together. We've already seen how this parallels the van der Waals interaction in chemistry. where neutral atoms attract through residual electromagnetic fluctuations. The Pion exchange picture now gives us the specific mechanism for the nuclear version of that effect. It tells us exactly what's being exchanged, what the exchanged object is made of, and why the force has the precise range it does. The analogy holds, but the Pion adds concrete detail that the analogy alone cannot provide. This is where the Pion enters the picture, because the residual strong force between nucleons, despite being complicated in its fundamental QCD description, can be elegantly and accurately described in terms of pion exchange. Just as the electromagnetic force between charged particles can be described as photon exchange, and just as Yukawa originally imagined, the effective nuclear force between protons and neutrons can be described as the exchange of pions. The pion is the carrier of the residual strong force, not the fundamental color force that's carried by gluons inside nucleons, but the leftover force, the residual interaction that leaks between color-neutral nucleons. This residual force is what holds every nucleus together, and it's carried by a particle that is itself a product of the color force, a quark-antiquark pair bound together by gluons, briefly flickering into existence between two nucleons and vanishing before the universe can notice it was ever there. So, to summarize the hierarchy clearly, because this distinction is essential, at the deepest level, quarks interact through the exchange of gluons. This is the fundamental strong force, the color force. It's described by quantum chromodynamics. It's incredibly powerful, and it's what binds quarks into protons and neutrons. But gluons and quarks are confined. They can't escape the nucleons they inhabit. At the next level up, protons and neutrons interact through the residual strong force. This is an effective force that arises because the internal color charge distribution of nucleons isn't perfectly uniform. It fluctuates, and those fluctuations can interact between neighboring nucleons. This residual force can be described effectively and accurately as the exchange of pions between nucleons. The pion is the effective carrier of this residual interaction. The residual strong force is what holds nuclei together, not gluons directly. Gluons are confined inside nucleons, not the full color force directly that operates only between quarks, but a leftover effect, a shadow, a residual leakage of the immensely powerful color force that operates within the quarks and gluons of each individual nucleon. And the particle that carries this residual effect, the messenger that shuttles between protons and neutrons and tells them to attract each other despite their electromagnetic repulsion, is the pion. A particle so short-lived that it exists for only the briefest flicker of time, so small that it operates on scales smaller than the nucleus itself, and so important that without it, no atom heavier than hydrogen could exist. No molecules, no chemistry, no stars, no planets, no life, nothing. Understanding the pion means understanding exactly how this residual force works, what the pion is made of, how it's exchanged, why it has the mass it has, why the force it carries has the range it has. And that's where we're going next. Because the pion isn't just any particle, it's a quark-antiquark pair, the lightest meson, a creature of the strong force that exists in 3 different charge states and mediates the most important interaction in all of nuclear physics. The interaction that holds matter together. So now we know the problem and we know the landscape. Gluons bind quarks inside protons and neutrons. They carry the fundamental color force. But gluons are confined. They can't escape the nucleons they live in. And yet, protons and neutrons attract each other powerfully enough to overcome electromagnetic repulsion and form stable nuclei. A residual effect of the color force leaks out between nucleons, creating an effective attraction at short range. And this residual force is carried by a particle called the pion. But what exactly is a pion? What is it made of? How does it carry the force? How does pion exchange actually work at the level of individual particles? And how did physicists figure all of this out? Let's start with what a pion is made of. A pion is a meson. That means it's a composite particle made of one quark and one antiquark, bound together by the strong force. Unlike a proton, which contains 3 quarks, a meson contains only 2, a quark and its antimatter partner. These 2 constituents are bound together by gluon exchange, the same color force that binds quarks inside protons and neutrons. But because there are only 2 constituents instead of 3, and because one of them is an antiquark, the properties of mesons are quite different from those of baryons like protons and neutrons. There are 3 types of pions, distinguished by their electric charge. The positive pion consists of an up quark and an anti-down quark, giving it a total charge of +1. The negative pion is its antiparticle, a down quark and an anti-up quark, with a total charge of -1. The neutral pion is a quantum mechanical mixture of an up quark paired with an anti-up quark and a down quark paired with an anti-down quark, giving it 0 net charge. The pions are remarkably light for composite particles made of quarks. The charged pions each have a mass of about 139.6 mega electron volts. The neutral pion is slightly lighter at about 135 mega electron volts. For comparison, the proton has a mass of about 938 mega electron volts. Pions are roughly 1/7 the mass of a proton, yet much heavier than electrons. They're the lightest mesons in existence. This lightness is not a coincidence. It's connected to a deep symmetry of the strong force called chiral symmetry. And the pions are what physicists call pseudo-Goldstone bosons, particles that arise when a symmetry is almost but not perfectly preserved. The details of chiral symmetry breaking are mathematically involved, but the important point is this. The pion's small mass is a direct consequence of the underlying structure of quantum chromodynamics. It's not arbitrary, it's dictated by the theory. And that mass, roughly 140 mega electron volts, is precisely what determines the range of the residual strong force between nucleons. We'll come back to that connection shortly. Now, pions are unstable. They don't last forever. The charged pions have a mean lifetime of about 26 nanoseconds, remarkably long by particle physics standards. A charged pion traveling at nearly the speed of light can cover about 8 meters before decaying. The neutral pion is much shorter lived, decaying in about 84 attoseconds into 2 gamma-ray photons. But here's the crucial thing. When we talk about pions mediating the nuclear force, we're not talking about real pions that are created, travel through space, and then get absorbed. We're talking about virtual pions. And virtual particles are a fundamentally different concept. In quantum field theory, forces between particles are described by the exchange of virtual particles. These virtual particles are not directly observable. They don't show up on detectors. They don't leave tracks. They exist as intermediate states in the mathematical description of the interaction, quantum fluctuations that are permitted by the uncertainty principle. The Heisenberg uncertainty principle tells us that there is a fundamental limit to how precisely certain pairs of quantities can be simultaneously known. One version of this principle relates energy and time. It states that a violation of energy conservation is permissible as long as it occurs for a sufficiently short period. Specifically, a fluctuation involving an energy delta E can persist for a time no longer than roughly h bar divided by delta E, where h bar is the reduced Planck constant. Creating a pion out of nothing requires energy equal to the pion's rest mass energy, about 140 mega-electron volts. The uncertainty principle allows this energy to be borrowed from the vacuum, but only for an extremely short time. How short? About 4.7 times 10 to the negative 24 seconds. In that tiny flicker of time, the pion can travel a distance of roughly 1.4 femtometers at most, even if it moves at nearly the speed of light. And there it is, the range of the nuclear force. The distance over which virtual pion exchange can operate is determined by the mass of the pion through the uncertainty principle. A heavier carrier particle would mean more energy borrowed, which means less time available, which means shorter range. A lighter carrier would mean less energy borrowed, longer time, longer range. A massless carrier, like the photon, can borrow zero energy and persist forever, which is why electromagnetism has infinite range. The pion's mass of about 140 mega-electron volts gives the residual strong force a range of about 1 to 2 femtometers. This matches perfectly with the observed range of the nuclear force. This was exactly Yukawa's insight in 1935, years before anyone knew about quarks or gluons or QCD. Yukawa didn't know that. The carrier particle would turn out to be a quark-antiquark pair. He didn't know about color charge or confinement, but he understood the deep connection between the mass of a force carrier and the range of the force it mediates. He knew the nuclear force had a range of about 1 to 2 femtometers. He used the uncertainty principle to calculate the mass the carrier must have. And he got it right, predicting the pion's mass more than a decade before it was discovered. Now, let's talk about how pion exchange actually produces a force between nucleons. This is where the picture becomes vivid, and where you can really start to see how the nucleus holds together. Imagine a proton and a neutron sitting near each other inside a nucleus, separated by a distance of about 1 or 2 femtometers. Inside the proton, 3 quarks are buzzing around, exchanging gluons, bound together by the color force. Inside the neutron, the same thing is happening with its own 3 quarks. Each nucleon is a self-contained system, color neutral from the outside. But remember, the internal structure of each nucleon is constantly fluctuating. Quarks are moving. Gluon fields are roiling. And in this churning environment, something can happen. One of the quarks inside the proton can emit a virtual pion. Specifically, one of the up quarks in the proton can emit a positive pion, a pi plus, which consists of an up quark and an anti-down quark. When the up quark emits this pion, it transforms into a down quark. Think about what just happened. The proton had 2 up quarks and 1 down quark. One of its up quarks turned into a down quark by emitting the pion. Now the proton has 1 up quark and 2 down quarks. That's no longer a proton. That's a neutron. The proton has become a neutron by emitting a positive pion. Meanwhile, the virtual pion, this fleeting quark-antiquark pair, travels the short distance to the neighboring neutron. The neutron absorbs the pion. When the neutron absorbs the Positive pion, one of its down quarks, absorbs the anti-down quark from the pion, and the up quark from the pion is incorporated into the nucleon. The neutron had 2 down quarks and 1 up quark. Now, after absorbing the pion, it has 1 down quark and 2 up quarks. That's a proton. The neutron has become a proton. So what has happened overall? The proton emitted a pion and became a neutron. The neutron absorbed the pion and became a proton. The 2 nucleons have exchanged identities. The proton became the neutron, and the neutron became the proton. And in the process, a force was transmitted between them. The exchange of the virtual pion created an attraction, pulling the 2 nucleons toward each other. This process can also happen in the other direction. The neutron can emit a negative pion and become a proton, while the proton absorbs the negative pion and becomes a neutron. Or either nucleon can emit a neutral pion without changing its identity. A proton can emit and reabsorb a neutral pion, or emit one that's absorbed by a neighboring proton or neutron. All of these processes contribute to the nuclear force. The total force between 2 nucleons is the sum of all possible pion exchange processes. Positive pions, negative pions, and neutral pions being exchanged in all possible ways. The exchange of charged pions is particularly interesting because it involves the nucleons swapping identities. This identity exchange is a uniquely quantum mechanical phenomenon. In classical physics, particles have definite identities that don't change. A proton is a proton, and a neutron is a neutron. But in quantum mechanics, if a proton and a neutron are close enough together and exchanging pions, you can't really say which one is the proton and which one is the neutron at any given moment. Their identities are blurred, shared, exchanged back and forth many times per second. The 2 nucleons become an entangled system where the labels proton and neutron become somewhat fluid and interchangeable. This charge exchange interaction is actually one of the strongest components of the nuclear force. It's the primary reason why nuclei with roughly equal numbers of protons and neutrons tend to be the most stable. The exchange of charged pions creates a strong attractive interaction between protons and neutrons that doesn't exist between 2 protons or 2 neutrons in the same way. This is why stable nuclei tend to have neutron to proton ratios close to 1 for light elements, though the ratio increases for heavier elements as the growing electromagnetic repulsion between protons requires additional neutrons to provide more nuclear binding without adding more repulsion. Now, there's something else important about the pion exchange force that distinguishes it from simple attraction. The nuclear force isn't just attractive. At very short distances, shorter than about half a femtometer, the force becomes repulsive. This short-range repulsion prevents nucleons from collapsing into each other. It creates a kind of hard core, a minimum distance that nucleons cannot get closer than. Without this repulsive core, nucleons would collapse on top of each other, and nuclear matter would shrink to a point. The repulsive core keeps nucleons at a comfortable distance, while the pion-mediated attraction at slightly larger distances keeps them from flying apart. The full nuclear force, including both the attractive part mediated primarily by pion exchange and the repulsive core at very short distances, is sometimes described by an effective potential called the nuclear potential. The most famous early model of this potential was developed by Yukawa himself, and more sophisticated versions were developed later by other physicists. These potentials describe the force between 2 nucleons as a function of their separation distance. At distances of about 1 to 2 femtometers, the potential is deeply attractive. At distances shorter than about half a femtometer, it rises steeply, becoming strongly repulsive. At distances beyond about 2 to 3 femtometers, it falls off exponentially to zero. This exponential fall-off is a direct signature of the Pion's mass. In Yukawa's theory, the potential between two nucleons has a characteristic form called a Yukawa potential. It decreases exponentially with distance, with the rate of decrease determined by the Pion's mass. The heavier the pion, the faster the potential falls off, and the shorter the range of the force. The Yukawa potential was one of the first successful applications of quantum field theory to nuclear physics, and it remains remarkably accurate for describing the nuclear force at moderate distances. It's worth pausing to appreciate how remarkable this whole picture is. The Pion, a particle that mediates the nuclear force, is itself a composite object made of quarks bound together by gluons. It's not a fundamental particle in the way that photons or gluons are. It's a bound state, a temporary pairing of a quark and an antiquark held together by the same color force that binds quarks inside protons and neutrons. And yet, this composite object serves as an effective force carrier for the interaction between nucleons. This is the layered nature of nuclear physics. At the deepest level, the fundamental force is the color force between quarks carried by gluons. This force confines quarks into protons, neutrons, and other composite particles. But it also creates the pion as a bound state of a quark and an antiquark, and the pion in turn mediates the residual strong force between nucleons, the force that builds atomic nuclei. The analogy with van der Waals forces bears repeating here because it really helps clarify what's happening. In electromagnetism, the fundamental force operates between individual charged particles, electrons, and protons. This force binds electrons to nuclei, creating atoms. Atoms are electrically neutral overall, but the residual electromagnetic interaction between neutral atoms, the van der Waals force, is what holds atoms together in molecules and liquids and solids. The van der Waals force is much weaker than the fundamental electromagnetic force, and it has much shorter range, but it's incredibly important for chemistry and biology and materials science. Similarly, in the strong interaction, the fundamental force operates between individual quarks carried by gluons. This force binds quarks into nucleons. Nucleons are color neutral overall, but the residual strong interaction between color neutral nucleons carried by pions is what holds nucleons together in atomic nuclei. This residual force is much weaker than the fundamental color force, and it has much shorter range, only a few femtometers. But it's incredibly important for nuclear physics. Without it, no nucleus heavier than hydrogen could exist. Without nuclei, there would be no elements, no chemistry, no stars, no planets, no life. The parallel is almost exact. Fundamental force creates bound states that are nominally neutral. Residual force leaks out between these neutral objects and creates the next level of structure. In electromagnetism, the hierarchy goes from charges to atoms to molecules. In the strong force, the hierarchy goes from color charges to nucleons to nuclei. The Pion plays the same role in nuclear binding that the van der Waals interaction plays in molecular binding. It's the bridge between levels. The thing that takes the effect of a confined fundamental force and transmits it to the next scale up. Now, I want to make something clear about the virtual pion exchange picture because it's easy to misunderstand. When I describe a proton emitting a virtual pion that travels to a neutron, I'm describing a process that happens in the mathematical framework of quantum field theory. I'm not describing a tiny ball being thrown from one nucleon to another like a game of catch. Virtual particles don't work quite like that. They're mathematical tools, terms in the equations that describe the interaction. The physical reality is the force, the attraction between nucleons. The virtual pion is the theoretical description of how that force arises in quantum field theory. That said, the virtual pion picture isn't just a mathematical trick. It has real, measurable consequences. The properties of the force it predicts, its range, its strength, its dependence on the nucleon's charges and spins, all of these match what's observed in experiments with extraordinary precision. The Pion exchange model has been tested against nuclear scattering data. The data from experiments where beams of protons or neutrons are fired at nuclear targets, and the pattern of scattered particles is measured. The agreement between theory and experiment is impressive, particularly at the intermediate distances of 1 to 2 femtometers, where pion exchange dominates. There's also direct experimental evidence for the importance of pions in nuclear interactions. When protons collide with each other or with neutrons at moderate energies, pions are among the most commonly produced particles. They're created in enormous quantities at particle accelerators. Their properties, mass, charge, spin, lifetime, decay modes have all been measured with great precision, and everything matches the predictions of the quark model and QCD. Pions also play a crucial role in nuclear reactions. In nuclear beta decay, where a neutron inside a nucleus transforms into a proton by emitting an electron and an antineutrino, the process is driven by the weak force, but the pion cloud surrounding each nucleon inside the nucleus modifies how the decaying nucleon interacts with that weak force, altering the precise rate and character of the decay. The pion cloud that surrounds each nucleon inside a nucleus affects how the nucleon interacts with the weak force, modifying the rate and characteristics of beta decay. Precision measurements of nuclear beta decay rates provide indirect evidence for the pion cloud's existence and properties. Let me talk about the experimental discovery of pions in more detail, because the story is both scientifically important and historically fascinating. After Yukawa's prediction in 1935, physicists began searching for his hypothetical meson. The initial confusion with the muon in 1936 delayed progress significantly. For more than a decade, many physicists believed the muon was Yukawa's particle, even though its behavior didn't match the prediction. The muon didn't interact strongly with nuclei. It passed through matter without being absorbed, which was completely inconsistent with being the carrier of the nuclear force. This discrepancy was puzzling, but not immediately resolved. The breakthrough came in 1947. Cecil Powell at the University of Bristol had developed a technique using specially prepared photographic emulsions that could record the tracks of individual charged particles. His team sent stacks of these emulsions to high-altitude locations where cosmic rays were more intense. Cosmic rays striking atoms in the upper atmosphere create showers of secondary particles, including pions. When Powell's team examined the developed emulsions, they found something remarkable. They saw tracks of particles that were clearly heavier than electrons but lighter than protons. More importantly, they saw these particles come to a stop in the emulsion and then decay into a lighter particle, which itself left a track. The heavier particle was the pion. The lighter particle it decayed into was the muon. The pion was created in the cosmic ray collision, traveled a short distance, and then decayed into a muon and a neutrino. The muon, being much less interactive with matter, then continued on, leaving its own longer track. This was the key observation. The pion and the muon were two different particles. The pion was heavier. It interacted strongly with nuclei. When it encountered a nucleus, it was quickly absorbed. The muon was lighter. It barely interacted with nuclei. It passed through matter with ease. The pion was Yukawa's particle. The muon was something else entirely. A particle that had nothing to do with the nuclear force. The confusion of the previous decade was resolved. Powell's discovery was confirmed rapidly by other groups. Within a year, pions were being produced artificially at the Berkeley cyclotron in California, the first particle accelerator powerful enough to create pions in the laboratory. Physicists could now study pions in controlled conditions, measuring their mass, charge, spin, and lifetime with increasing precision. Every measurement confirmed that the pion was exactly what Yukawa had predicted. The discovery also revealed that there were three types of pions: the positively charged pi plus, the negatively charged pi minus, and the electrically neutral pi zero. The charged pions were discovered first in cosmic rays and then produced at accelerators. The neutral pion was harder to find because it's electrically neutral and therefore doesn't leave a track in emulsions or cloud chambers. It was finally detected in 1950 through its characteristic decay into two gamma rays. All three pion types contribute to the nuclear force. The exchange of charged pions is responsible for the charge exchange interaction I described earlier, where protons and neutrons swap identities. The exchange of neutral pions contributes to the nuclear force without changing the identities of the nucleons. Together, these three exchange processes produce the full nuclear potential that binds protons and neutrons together in the nucleus. There's one more aspect of the pion's role I want to emphasize before we move on. The pion isn't the only meson that contributes to the nuclear force. At shorter distances, heavier mesons also play a role. Particles like the RHO meson, with a mass of about 775 mega-electron volts, and the omega meson, with a mass of about 783 mega-electron volts, contribute to the nuclear force at distances shorter than about 1 femtometer. The RHO meson in particular is responsible for much of the short-range repulsion, the hard core that prevents nucleons from collapsing into each other. In the most complete models of the nuclear force, called one-boson exchange models, the full nuclear potential is described as the sum of exchanges of several different mesons. Pions dominate at the longest range, from about 1 to 2 femtometers. Sigma mesons and other scalar particles contribute at intermediate range, around 1 femtometer. Rho and omega mesons contribute at short range, below 1 femtometer. Each meson contributes a Yukawa-type potential with a range determined by its mass. The heavier the meson, the shorter the range of its contribution. But among all these mesons, the pion holds a special place. It's the lightest. It has the longest range, and it provides the dominant attraction at the distances where nuclear binding is established. Without pion exchange, the other meson exchanges would not produce enough attraction to bind nucleons into stable nuclei. The pion is the essential ingredient, the particle whose exchange makes nuclear physics possible. So now the full mechanism stands clear. We already understand the layers. Gluons confined inside nucleons, the color force locked away behind a neutral boundary. What the Pion adds is the bridge. It's the specific physical object that crosses the gap between one nucleon and another. Not a gluon, which can't escape, but a quark-antiquark pair that the color force itself creates, and then briefly releases into the space between nucleons. The Pion exists because confinement isn't quite perfect at nuclear distances. A trace of the color force leaks through, and it leaks through in the form of the lightest possible quark-antiquark combination. And yet, when two nucleons come within a few femtometers of each other, something happens. The internal structure of each nucleon, the fluctuating distribution of quarks and gluons inside, creates a residual interaction. This interaction can be described elegantly and accurately as the exchange of virtual pions between the nucleons. The pion itself, a quark-antiquark pair bound by the color force, serves as the effective carrier of this residual interaction. It hops from one nucleon to another, existing for a fleeting instant permitted by the uncertainty principle, transmitting an attractive force that overcomes electromagnetic repulsion and binds the nucleus together. Without gluons, there would be no protons or neutrons. Without pions, there would be no nuclei. The gluon builds the bricks, the pion is the mortar, and together they construct every atom in the universe heavier than hydrogen. Every atom of helium that formed in the first few minutes after the Big Bang. Every atom of carbon forged in the cores of dying stars. Every atom of oxygen in the air you're breathing right now. Every atom of iron in your blood, of calcium in your bones, of phosphorus in your DNA. All of it held together at the nuclear level by the exchange of virtual pions, flickering in and out of existence for the briefest imaginable instant, carrying a force borrowed from the deepest level of physical reality. So now we understand the mechanism. Pions carry the residual strong force between nucleons. Virtual pion exchange produces the attraction that overcomes electromagnetic repulsion inside the nucleus. But understanding the mechanism is only the beginning, because the consequences of this mechanism reach far beyond the nucleus itself. The specific properties of the pion-mediated force, its strength, its range, the way it falls off with distance, these properties determine the size and stability of every atomic nucleus in the universe. They determine which elements can exist and which cannot. They determine why stars shine, why supernovae explode, why the periodic table has the structure it does, and ultimately why the universe contains the particular mix of elements that makes life possible. Let's start with range, because the range of the nuclear force is perhaps its most consequential property. We've established that the pion's mass, roughly 140 mega-electron volts, gives the residual strong force a range of about 1 to 2 femtometers. Beyond that distance, the force drops off exponentially, falling to essentially zero within about 3 femtometers. This is in stark contrast to electromagnetism, which drops off as the inverse square of distance, but never actually reaches zero. No matter how far apart two charged particles are, they still feel each other's electromagnetic influence, however weakly. This difference between infinite range electromagnetic repulsion and short range nuclear attraction has profound consequences for nuclear structure. Consider a small nucleus, like helium-4, which contains 2 protons and 2 neutrons. In this tiny nucleus, every nucleon is within about 1 to 2 femtometers of every other nucleon. All 4 particles can feel the strong attractive force from all 3 of their neighbors. The total nuclear attraction far outweighs the electromagnetic repulsion between the 2 protons. the nucleus is tightly and stably bound. Helium-4 is in fact one of the most tightly bound nuclei in nature. Its binding energy per nucleon, the average energy holding each nucleon in place, is about 7.1 mega electron volts. This is high, and it makes helium-4 extraordinarily stable. Now, consider what happens as you add more nucleons to build heavier nuclei. At first, the binding gets tighter. As you go from helium to carbon to oxygen to silicon, the binding energy per nucleon generally increases. Each new nucleon you add feels the strong attractive force from its immediate neighbors, adding to the total binding. But there's a crucial limitation. Because the nuclear force has a range of only about 1 to 2 femtometers, each nucleon can only interact strongly with its nearest neighbors. It can't reach across the entire nucleus to attract nucleons on the far side. A nucleon in a carbon-12 nucleus with a radius of about 2.7 femtometers can feel the strong force from most of the other nucleons because the nucleus is small enough. But a nucleon in a uranium-238 nucleus, which has a radius of about 7.4 femtometers, can only feel the strong force from nucleons within a few femtometers of it. The nucleons on the opposite side of the nucleus are too far away. They're beyond the range of pion exchange. Electromagnetism, on the other hand, has no such limitation. Every proton in the nucleus feels the electromagnetic repulsion from every other proton, regardless of distance. In a heavy nucleus like uranium, every single proton repels every other proton across the full diameter of the nucleus. Thousands of repulsive pairs are all contributing simultaneously, and the electromagnetic force between each pair reaches across the entire nuclear volume regardless of distance. So as nuclei get larger, an imbalance develops. The strong attractive force, being short range, only grows in proportion to the number of nearest neighbors each nucleon has. Once the nucleus is large enough that nucleons in the interior are fully surrounded by neighbors, adding more nucleons to the surface doesn't significantly increase the average attraction per nucleon. The electromagnetic repulsion, however, keeps growing because every new proton added repels all the other protons across the entire nucleus. The repulsion grows faster than the attraction. This is why the binding energy per nucleon doesn't keep increasing forever. It rises from hydrogen through helium through carbon, reaches a peak in the vicinity of iron and nickel, and then slowly decreases for heavier elements. Iron 56 and nickel 62 have the highest binding energy per nucleon of any nucleus, about 8.8 mega electron volts per nucleon. These are the most tightly bound nuclei in nature. They sit at the sweet spot where the short-range nuclear attraction and the long-range electromagnetic repulsion are optimally balanced. This binding energy curve, this rise and fall of nuclear stability across the periodic table, is one of the most important graphs in all of physics, and it's a direct consequence of the pion's mass. If the pion were lighter, the nuclear force would have longer range. Nucleons could attract each other across larger distances. The binding energy peak would shift to heavier elements. Nuclei could be larger and still remain stable. If the pion were heavier, the nuclear force would have shorter range. Even moderate-sized nuclei would become unstable because the attraction couldn't extend far enough to overcome the repulsion. Fewer elements could exist. The periodic table would be shorter. The binding energy curve directly explains why nuclear fusion releases energy for light elements, and why nuclear fission releases energy for heavy elements. And both of these processes are consequences of pion exchange and its limited range. Fusion is the process of combining light nuclei into heavier ones. When two hydrogen nuclei fuse to form helium, the resulting helium nucleus is more tightly bound than the original hydrogen nuclei. The binding energy per nucleon increases. The difference in binding energy is released as kinetic energy of the products, as radiation, as the energy that powers stars. This process continues to release energy as long as you're building nuclei lighter than iron. Each step up the periodic table, from hydrogen to helium, to carbon, to oxygen, to silicon, to iron, releases energy because you're moving toward the peak of the binding energy curve. You're creating more tightly bound nuclei from less tightly bound ones. This is why stars shine. In the core of our sun, hydrogen nuclei are being fused into helium at a rate of about 600 million tons of hydrogen every second. The resulting helium is slightly less massive than the original hydrogen. The missing mass has been converted into energy according to Einstein's equation, E equals mc squared. This energy is what makes the sun hot. It's what produces the sunlight that warms Earth and makes life possible. And it all comes from the nuclear binding energy curve. It all comes, ultimately, from the properties of pion exchange. Heavier stars burn through successive fuels, fusing helium into carbon, carbon into oxygen, and onward through progressively heavier elements. Each step releasing energy as it moves closer to the binding energy peak. But when the core reaches iron, fusion stops releasing energy. Iron is at the peak. Fusing it into heavier elements would require energy input rather than releasing it. Iron is at the peak. Fusing iron into heavier elements would require energy input rather than releasing energy, because you'd be moving away from the peak, creating less tightly bound nuclei from more tightly bound ones. This is why massive stars develop iron cores. They burn through fuel after fuel, each stage shorter than the last, until they reach iron and can go no further. The iron core grows until it reaches a critical mass, about 1.4 solar masses, called the Chandrasekhar limit. At that point, the core can no longer support itself against its own gravity. It collapses in a fraction of a second, falling inward at speeds up to 70,000 kilometers per second. The collapse triggers a supernova, one of the most violent events in the universe, briefly outshining the entire galaxy that contains it. And here's the connection to the elements heavier than iron. During the supernova explosion, conditions become so extreme, temperatures of billions of degrees, pressures beyond imagination, that nuclear reactions can proceed that don't normally occur. Elements heavier than iron can be forged in these extreme conditions, not through fusion, but through rapid neutron capture, a process called the R process. Neutrons slam into existing nuclei so fast that the nuclei don't have time to decay between captures. They build up to enormous masses, eventually undergoing beta decay to convert some of their neutrons into protons, creating stable heavy elements. This is how gold, platinum, uranium, and all the other elements heavier than iron were created. Not in the steady burning of stellar cores, but in the violent deaths of massive stars. Every atom of gold in every ring and necklace on Earth was forged in a supernova explosion billions of years ago. And the reason this process was necessary, the reason these elements couldn't be made by ordinary fusion, is the binding energy curve. And the binding energy curve exists because of the short range of the nuclear force. And the short range of the nuclear force exists because the pion has mass. Now, let's look at the other side of the binding energy curve. Fission. Heavy nuclei, those heavier than iron, are less tightly bound than iron. They're held together, but just barely. The electromagnetic repulsion between their many protons is almost strong enough to tear them apart. They're on the edge of instability. For the heaviest naturally occurring elements, like uranium and thorium, this instability becomes pronounced. Uranium 235, with 92 protons and 143 neutrons, is fissile. If it absorbs a neutron, it becomes uranium 236, which is so unstable that it splits apart into two smaller nuclei, plus a few free neutrons. The two smaller nuclei, called fission fragments, are closer to the peak of the binding energy curve than uranium is. They're more tightly bound. The difference in binding energy is released as kinetic energy of the fragments and radiation. The energy released by a single uranium fission event is about 200 mega electron volts. Per atom, that sounds modest, but a kilogram of uranium-235 contains about 2.5 times 10 to the 24 atoms. Fission, all of them, and release energy roughly equivalent to 20,000 tons of TNT. This is the basic principle behind nuclear reactors and nuclear weapons. And all of it traces back to the binding energy curve. Fission releases energy because heavy nuclei are less tightly bound than medium-weight nuclei. Heavy nuclei are less tightly bound because the short-range nuclear attraction can't keep up with the long-range electromagnetic repulsion in large nuclei. The nuclear attraction is short-range because the pion has mass. Everything connects. The properties of a single subatomic particle, the pion, determine the energy output of nuclear reactors, the destructive power of nuclear weapons, the reason stars shine, the process by which heavy elements are created, and the structure of the entire periodic table. Let me push this even further. The short range of the nuclear force doesn't just determine which nuclei are stable. It determines how large nuclei can be. There's a limit to the size of the periodic table, and that limit exists because of pion exchange. As you build heavier and heavier nuclei by adding more protons and neutrons, the electromagnetic repulsion between protons keeps growing. At some point, the repulsion becomes so strong that no arrangement of nucleons can create a stable nucleus. The strong force simply can't hold the nucleus together anymore. For naturally occurring elements, this limit is effectively reached at uranium, element 92. Beyond uranium, elements must be synthesized in laboratories or are produced only in trace amounts through natural radioactive processes. And the heavier you go, the less stable these elements become, many of them fantastically so, with lifetimes measured in milliseconds or even microseconds. Physicists have theorized that there might be an island of stability, a region of the periodic table around element 114 or 120 where certain combinations of protons and neutrons might form relatively stable nuclei due to quantum mechanical shell effects. Some of these super heavy elements have indeed been created, and a few show slightly longer lifetimes than their neighbors. But even the most optimistic predictions suggest these nuclei would survive for seconds or minutes at most, not the billions of years required for practical stability. The short range of the nuclear force sets a hard limit on how complex nuclear matter can be. The pion-mediated force doesn't just determine which nuclei are stable, it determines the detailed internal structure of nuclei in ways that produce striking patterns observable across the entire periodic table. one of us, and the most remarkable of these patterns is the existence of nuclear magic numbers. Physicists noticed decades ago that nuclei with certain specific numbers of protons or neutrons are anomalously stable. These special numbers are 2, 8, 20, 28, 50, 82, and 126. Nuclei that have one of these magic numbers of protons or neutrons are more tightly bound than their neighbors on the periodic table. They're harder to break apart. They're more abundant in nature. And they have higher energy thresholds for excitation, meaning you need to pump in more energy to disturb their internal structure. Helium-4, with 2 protons and 2 neutrons, is doubly magic. Both its proton number and its neutron number are magic numbers. This double shell closure is the deeper reason behind the exceptional binding we discussed earlier, and it explains why helium-4 is emitted as a single unit, an alpha particle, in many forms of radioactive decay. Oxygen-16, with 8 protons and 8 neutrons, is another doubly magic nucleus. Lead-208, with 82 protons and 126 neutrons, is the heaviest stable, doubly magic nucleus. It's also the heaviest stable nucleus of any kind, sitting right at the edge beyond which all elements are radioactive. These magic numbers arise because nucleons inside the nucleus occupy quantized energy levels, similar to how electrons occupy quantized energy levels in atoms. Just as electrons fill atomic shells, with noble gases representing completely filled electron shells and therefore exceptional chemical stability, nucleons fill nuclear shells. When a nuclear shell is completely filled, the nucleus is especially stable. The magic numbers correspond to complete nuclear shell closures. But here's the connection to pions. The shape of these nuclear energy levels, the spacing between them, the order in which they fill, all of this is determined by the nuclear potential. And the nuclear potential is determined by pion exchange. The attractive force at 1 to 2 femtometers, the repulsive core at very short distances, the spin and isospin dependence of the pion-mediated interaction. All of these features of the pion exchange force shape the potential well in which nucleons move. Change the pion's mass and you'd change the range of the force, which would change the shape of the potential, which would change the energy levels, which would change the magic numbers. Different magic numbers would mean different patterns of nuclear stability, different abundances of elements in nature, a different periodic table entirely. In particular, the spin-orbit component of the nuclear force, where the force depends on whether a nucleon spin is aligned or anti-aligned with its orbital motion inside the nucleus, is crucial for producing the correct magic numbers. This spin-orbit coupling was identified by Maria Goeppert-Mayer and independently by Hans Jensen in 1949, a discovery that earned them the Nobel Prize in 1963. The spin-orbit force arises naturally from the exchange of vector mesons, like the RH and omega mesons, the heavier cousins of the pion that contribute to the nuclear force at shorter range. Without this spin-orbit coupling, the nuclear shell model would predict different magic numbers that don't match observation. The correct magic numbers emerge only when the full meson exchange potential, including both pions and heavier mesons, is taken into account. The magic numbers are not just theoretical curiosities, they have real consequences for the universe. The elements that are most abundant in nature, the elements that make up the bulk of rocky planets and the cores of stars, tend to cluster around magic numbers. Nickel, with 28 protons, sits exactly at a magic number. Iron, with 26 protons, sits just below that same magic number. Both elements owe their exceptional cosmic abundance in part to this proximity to a closed nuclear shell. The elements produced in the R process during supernovae show abundance peaks that correspond to the magic numbers. Because nuclei with filled shells are more resistant to further neutron capture and serve as waiting points where material accumulates during the rapid synthesis of heavy elements. So the Pion doesn't just determine that nuclei exist, it determines the specific pattern of which nuclei are most stable, which elements are most abundant, and how the periodic table is structured in detail. The fingerprints of Pion exchange are written across the entire chart of the Nucleides. There's another extreme consequence of the Pion-mediated force that deserves attention. What happens when you take nuclear matter to its ultimate limit? What happens when you compress so many nucleons together that you have not a nucleus of a few hundred particles, but a nucleus of 10 to the 57 particles? What you get is a neutron star. A neutron star is what remains after a massive star exhausts its nuclear fuel and its core collapses in a supernova explosion. The core is compressed so violently that electrons are forced into protons, converting them into neutrons through a process called inverse beta decay. The result is an object about 12 to 14 kilometers across, roughly the size of a city, containing about 1.4 to 2 times the mass of our Sun. A neutron star is, in essence, a giant atomic nucleus. Not literally, because it's held together primarily by gravity rather than the nuclear force, but the matter inside it is nuclear matter. Neutrons pack together at nuclear density, about 2.3 times 10 to the 17 kilograms per cubic meter. A teaspoon of neutron star material would weigh over 1 billion tons on Earth. Inside a neutron star, the Pion-mediated force plays a critical role. The neutrons are packed so closely together that they interact through the same short-range nuclear force that operates inside ordinary nuclei. The repulsive core of the nuclear force, the part that prevents nucleons from collapsing on top of each other at distances shorter than about 0.7 femtometers, is what provides much of the pressure that supports the neutron star against gravitational collapse. Without this repulsive core, which arises from the exchange of heavy vector mesons like the RHO and omega, neutron stars would collapse further, potentially forming black holes at much lower masses than they actually do. The attractive part of the nuclear force, mediated primarily by Pion exchange, also matters inside neutron stars. At the extreme densities found in neutron star interiors, Pion exchange can potentially lead to exotic states of matter. Physicists have theorized that at sufficiently high densities, a Pion condensate might form, a coherent field of pions that would dramatically alter the neutron star's cooling rate, maximum mass, and structural properties. Whether this occurs is still debated because the physics involves the interplay of the strong force, quantum mechanics, and general relativity at extreme conditions no laboratory on Earth can reproduce. But the very fact that this is a serious area of research tells you something about the Pion's importance. It's not just relevant to ordinary nuclei, it's relevant to some of the most extreme objects in the universe, objects where matter is compressed to densities that test the limits of our understanding of physics itself. Neutron stars are also where the nuclear force meets gravity in the most dramatic way possible. Inside an ordinary nucleus, gravity is completely irrelevant, trillions of times too weak to matter. But inside a neutron star, Gravity is so strong that it compresses nuclear matter to its limits. The nuclear force, carried by a pion exchange and heavier meson exchange, provides the pressure that resists this gravitational compression. The structure of a neutron star, its mass, its radius, its density profile, is determined by the balance between gravity pulling inward and nuclear pressure pushing outward. And that nuclear pressure is ultimately a consequence of the same pion-mediated interactions that hold together the nucleus of every atom in your body. So the pion's influence extends from the smallest bound nuclei, from helium and lithium and beryllium, all the way up to neutron stars, objects containing more nucleons than all the atoms on Earth combined. From the scale of femtometers to the scale of kilometers. From the lightest elements to the densest objects in the universe. The same force, the same exchange mechanism, the same borrowed quark-antiquark pair, conjured from the vacuum for the briefest possible instant, operating across this entire range, building structure at every scale. Now, I want to address something important about the modern understanding of pion exchange and its relationship to QCD, because while the pion exchange picture is powerful and accurate, it's also, in a deep sense, an approximation. An incredibly useful and remarkably precise approximation, but an approximation nonetheless. The fundamental theory of the strong interaction is quantum chromodynamics, QCD. In QCD, there are no pions at the fundamental level. There are only quarks and gluons interacting through the color force. The pion emerges as a composite object, a bound state of a quark and an antiquark. And the nuclear force between nucleons, described in the pion exchange picture as the exchange of virtual pions, is in QCD described as a complex multi-gluon interaction between the quarks in neighboring nucleons. In principle, if you could solve QCD exactly, you wouldn't need pions at all. You could calculate the force between two nucleons directly from the quark and gluon dynamics. You'd start with 6 quarks, 3 in each nucleon, interacting through gluon exchange, and you would compute the resulting force. Practice. This is extraordinarily difficult. The QCD equations that describe the interaction between quarks and gluons are nonlinear and strongly coupled at nuclear energy scales. You can't solve them with pencil and paper. You can't even solve them with simple computer programs. The only way to extract predictions from QCD at nuclear energy scales is through lattice QCD, the technique where space and time are discretized into a grid, and the equations are solved numerically on supercomputers. Lattice QCD has made remarkable progress in recent decades. Physicists have used it to calculate the masses of protons, neutrons, and pions from first principles, starting with nothing but the quark masses and the coupling constant of QCD. The results match experimental measurements beautifully. Lattice. QCD has also been used to calculate the force between two nucleons, reproducing the essential features of the nuclear potential, the attraction at 1 to 2 femtometers, the repulsive core at very short distances, the exponential falloff at longer ranges. These lattice QCD calculations confirm what the pion exchange model has been telling us for decades. The nuclear force between nucleons really is a residual effect of the color force between quarks. The pion exchange description is an accurate effective theory that captures the essential physics of this residual interaction. It's not the fundamental description QCD is, but it's an excellent approximation that works beautifully at nuclear distance scales. This is actually a common pattern in physics. You have a fundamental theory that's complete and correct, but very difficult to work with. And you have an effective theory that's simpler and more practical, that captures the essential physics at the relevant scale, even though it's technically an approximation. Newtonian gravity is an effective theory that approximates general relativity. Thermodynamics is an effective theory that approximates statistical mechanics. And Pion exchange is an effective theory that approximates QCD at nuclear scales. The fact that Pion exchange works so well as an approximation is itself remarkable. It tells us something deep about how nature is organized. The strong force operates at the quark level, but its effects propagate upward through layers of organization, from quarks to nucleons to nuclei, in ways that can be captured by effective descriptions at each level. The pion is the bridge between the quark level and the nuclear level. It's the effective degree of freedom that transmits the residual color force from one nucleon to another. This layered structure of nature, where the physics at each scale can be described by its own effective theory without needing to know all the details of the deeper level, is one of the most beautiful and practical features of the physical world. You don't need to solve QCD to understand nuclear physics. You just need pions. You don't need to understand nuclear physics to understand chemistry. You just need atoms. Each level provides the building blocks for the next, and the details of the lower level are hidden, abstracted away, replaced by effective descriptions that capture what matters at the current scale. Let me step back now and reflect on what we've covered in its entirety. Because the story of the Pion and the nuclear force is really a story about how the universe builds complexity from simplicity, how the deepest forces of nature create the structures that make everything possible. At the most fundamental level we currently understand, there are quarks and gluons interacting through the color force described by QCD. This force is extraordinarily powerful, the strongest force in nature. It confines quarks permanently inside composite particles. It generates the mass of protons and neutrons through sheer binding energy. And it operates on scales of less than 1 femtometer, smaller than the nucleus itself. From this fundamental interaction, composite, particles emerge, protons and neutrons, each made of 3 quarks bound by gluons. These nucleons are color neutral from outside. The color force is confined within them, but a residual effect leaks out, a shadow of the color force that extends just barely beyond the nucleon's boundary. This residual effect is carried by pions, the lightest mesons, themselves made of quark-antiquark pairs bound by gluons. Virtual pions are exchanged between neighboring nucleons, transmitting an attractive force that overcomes electromagnetic repulsion at distances of 1 to 2 femtometers. This is the force that builds atomic nuclei. The properties of this pion-mediated force, particularly its short range, determined by the pion's mass, shape the entire landscape of nuclear physics. They determine the binding energy curve, which peaks at iron and falls off for both lighter and heavier elements. This curve determines that fusion of light elements releases energy, powering stars and forging elements up to iron. It determines that fission of heavy elements releases energy, making nuclear power and nuclear weapons possible. It determines that elements heavier than iron require the extreme conditions of supernovae or neutron star mergers to be created. And it determines the upper limit of the periodic table, the maximum number of protons that can coexist in a single nucleus. Every atom in the universe, heavier than hydrogen, owes its existence to this chain of physics. The carbon in your cells was forged by nuclear fusion in the core of a star that died billions of years ago. The oxygen you're breathing was created the same way. The iron in your blood was produced at the endpoint of stellar fusion, the peak of the binding energy curve. The calcium in your bones, the potassium in your nerves, the phosphorus in your DNA, all of it was synthesized in stellar cores or stellar explosions, in processes governed by the binding energy curve, which is in turn governed by the properties of Pion exchange. And every single one of those atoms is held together right now, at this very moment, by the residual strong force. The nuclei of every atom in your body are bound by virtual pion exchange. Quarks inside your protons and neutrons are exchanging gluons billions of times per second. Between your nucleons, virtual pions are flickering in and out of existence, borrowing energy from the vacuum for the briefest instance permitted by the uncertainty principle, carrying the attractive force that keeps your nuclei intact. If you could somehow switch off pion exchange, every nucleus in the universe would fly apart. Every atom would disintegrate into a cloud of isolated protons and electrons. There would be no elements, no molecules, no chemistry. Stars would be impossible because stellar fusion requires nuclei to exist and interact. Planets would be impossible because planets are made of atoms. Life would be impossible because life requires complex chemistry built on a diverse periodic and table. The universe would be nothing but a diffuse gas of protons, neutrons, and electrons, forever unable to combine into anything more complex. This is the weight that rests on the Pion's shoulders. A particle that most people have never heard of. A particle that exists for only 26 nanoseconds in its charged form, and a fraction of an attosecond in its neutral form. A particle that was predicted before it was discovered. That confused physicists for a decade before it was properly identified. That turned out to be not fundamental, but composite. A temporary pairing of a quark and an antiquark held together by the same force it's responsible for transmitting. The Pion is not flashy. It doesn't have the fame of the photon or the mystique of the Higgs boson. It's rarely mentioned in popular science, but in terms of its importance to the structure of the universe, it is second to nothing. Without the photon, there would be no light, no electromagnetism, no chemistry in the way we know it. Without the gluon, there would be no protons, no neutrons, no nuclear matter at all. And without the pion, there would be no nuclei, no bridge between individual nucleons and the complex atomic structures that make up everything we see and touch and are. The next time you look at anything, a tree, a rock, a star in the night sky, your own hand, remember what's happening inside. At the deepest level, quarks are bound by gluons, locked away in protons and neutrons by the most powerful force in nature. And between those protons and neutrons, virtual pions are being exchanged in a ceaseless quantum dance, holding the nucleus together against electromagnetic repulsion, building the atoms that build the molecules that build the world. A quark-antiquark pair, flickering in and out of existence for the most fleeting instant imaginable, carrying a force borrowed from the deepest level of reality. That's what a pion is. And that's why the nucleus stays together. That's why atoms exist. That's why you exist. Everything you've ever seen, everything you've ever touched, every star that has ever burned, every planet that has ever formed, every living thing that has ever drawn breath, all of it depends on this one borrowed interaction. a residual whisper of the strongest force in the universe, carried by the lightest meson, operating on a scale smaller than the atom itself, for a duration shorter than thought, holding everything together. That is the Pion. And now you know why it matters.